Hello everyone, and welcome to today's presentation on pipe wall thickness calculation. I'm excited to have you here. Today, we'll explore how to determine the required wall thickness, choose the proper schedule, and ensure compliance with industry standards. The focus will be on the ASME B31.3 process piping code, which guides our practices. You'll also notice the logos of ASME, API, and NACE, highlighting the standards and organizations involved. Over the next few slides, we'll cover key concepts and practical approaches to piping wall thickness. Let's get started. Let's talk about the purpose and importance of controlling thickness in pressure containment. Thickness is critical because it directly impacts safety. If the material is too thin, there's a risk of leaks or even bursts, which can be dangerous and lead to failures. On the other hand, if it's too thick, we end up with unnecessary costs and added weight, which can be inefficient and impractical. The key is finding the right balance, what we call the correct thickness. Achieving this balance ensures that we maintain safety standards while also being economical. This concept ties into the overall goal of designing safe, cost-effective pressure vessels and systems. Let's take a moment to understand pipe dimensions. Pipes are typically defined by two main factors: the nominal pipe size, or NPS, and the schedule number. The NPS gives us a general idea of the pipe's size, but it's not the exact measurement of the pipe's actual dimensions. Instead, it's a standardized designation. Now, the schedule number plays a crucial role because it indicates the wall thickness of the pipe. A higher schedule means a thicker wall, which in turn allows the pipe to withstand higher pressure ratings. This is important when selecting the right pipe for different applications, especially in high-pressure systems. Finally, it's worth noting that these dimensions and standards are not arbitrary. They are standardized through established codes, specifically ASME B3610 for carbon steel pipes and B3619 for stainless steel pipes. This standardization helps ensure consistency, safety, and compatibility across the industry. So, understanding these key concepts, NPS, schedule number, and the relevant standards, helps us ensure we choose the right pipe for the right application, ensuring safety and performance throughout the system. Let's take a closer look at some key ASME standards that are fundamental to our industry. First, we have ASME B31.3, which sets the design rules specifically for process piping. This standard ensures that our piping systems are safe, reliable, and efficient under the operating conditions they face. Next, ASME B3610 and B3619 address pipe sizes and schedules. These standards are essential for selecting the right pipe dimensions and wall thicknesses for different applications, helping us maintain consistency and safety. Then, there's ASME section IID, which provides allowable stress values. Understanding these stress limits is crucial for designing components that won't fail under pressure or temperature stresses. We also have ASME section VIII, focusing on external pressure design. This standard guides us on how to prevent pipe or vessel collapse when subjected to external forces. Finally, the B16 series covers fittings, flanges, and valves. These fittings are vital connections that ensure our piping systems are sealed and function properly under various operating conditions. All of these standards work together to support safe, efficient, and reliable piping and pressure vessel designs, reinforcing the overall theme of safety and quality in our projects. Today, I'll be discussing some of the key standards that underpin our industry practices. First, let's look at API 5L and ISO 3183, which define the specifications for line pipe materials. These standards ensure that the pipes we use are reliable and suitable for transporting oil and gas over long distances. Moving on, API 570 is crucial for in-service inspection and re-rating, helping us maintain safety and performance throughout the pipeline's operational life. Next, API RP 574 provides guidelines for corrosion monitoring, which is essential for preventing failures caused by corrosion, especially in harsh environments. We also have API 610 and 617, which set the interface requirements for pumps and compressors, ensuring these critical components work seamlessly together. When it comes to materials exposed to sour gases, NACE Mr. 0175 and ISO 15156 are vital, as they specify the allowable materials for H2S-containing environments, protecting both equipment and personnel. Lastly, NACE SB0169 focuses on cathodic protection for buried piping, a technique that helps prevent corrosion from underground exposure. All of these standards collectively support our goal of safe, reliable, and efficient operations, aligning with the overall theme of maintaining integrity across our systems. Let's talk about the design concept for pipe thickness. The key idea here is that the thickness isn't just a fixed number. It actually depends on several critical factors. These include the pressure the pipe will handle, the temperature conditions it will face, the material strength, and the quality of the welds. All of these influence how thick the pipe needs to be to remain safe and reliable. Additionally, we need to consider allowances for corrosion and threading, since these can weaken the pipe over time. Once we perform our initial calculations, it's important to select the next higher standard schedule. This provides a margin of safety, ensuring the pipe can handle unexpected variations or future conditions. Finally, after choosing the appropriate schedule, we must verify that the selected pipe can indeed handle the design pressure. This step confirms that our choice is both practical and safe, aligning with the overall goal of a robust and reliable piping system. Let's walk through this example calculation together. Imagine we have a 12-inch carbon steel pipe operating at 550 psi and a temperature of 700 degrees Fahrenheit. Based on our calculations, the required pipe thickness comes out to approximately 0.33 inches. Now, to ensure durability and account for corrosion over time, we add a corrosion allowance of about 0.12 inches. When we combine these, the total thickness we need is around 0.45 inches. Looking at standard pipe schedules, the nearest match is Schedule 40, which is widely available and suitable for this application. This example highlights a key point. By doing these calculations carefully, we ensure our piping is both safe for the operating conditions and accessible in the market. It's a practical demonstration of how engineering principles translate into real-world, reliable piping design. Let's talk about external pressure and bends in piping systems. When a pipe is subjected to vacuum or external pressure, it can become vulnerable to collapsing if the pipe wall is too thin. That's why it's crucial to check the pipe's strength carefully. I recommend using the ASME section VIII charts to ensure the pipe can handle these stresses safely. Another key point is limiting the amount of bend thinning to about 10%. This helps maintain the pipe's structural integrity. Additionally, ovality, which is the deviation from a perfect circle, should be kept within 8% to prevent weak spots. Finally, when designing pipes, we shouldn't forget about flexibility and thermal expansion. These factors are vital because they influence how the pipe responds to temperature changes and mechanical stresses over time. Incorporating these considerations ensures a safer, more reliable piping system that can withstand external pressures and bends effectively. Let's now move on to the installation and field practice phase. First, it's crucial to verify all pipe markings and the schedule before starting installation. This ensures we're working with the correct specifications and helps avoid costly mistakes later. Next, we need to align supports, anchors, and guides properly. Proper alignment is key to maintaining the integrity and safety of the piping system throughout its operational life. We also have to account for thermal expansion. Using loops and flex connectors allows the pipe to expand and contract naturally with temperature changes, preventing stress and potential damage. When it comes to welding, only qualified welders should perform the work, and it must be done according to ASME IX standards to guarantee quality and safety. Following welding, inspection is essential. Techniques like radiography or ultrasonic testing help verify the welds are sound and free from defects. After that, applying coating and cathodic protection, following NACE SB0169 guidelines, protects the pipe from corrosion and extends its service life. Finally, we conduct a hydro test at 1.5 times the design pressure. This test confirms the system's integrity under pressure, and recording the baseline thickness helps monitor for any future corrosion or wear. All these steps are interconnected and vital to ensure a safe, durable, and reliable piping installation. Let's conclude with some key points to keep in mind as we move forward. First, always follow the ASME B31.3 code for your design rules. This ensures your piping systems are safe and compliant. When determining allowable stresses, refer to ASME IID, which provides the necessary stress limits for different materials. It's also crucial to check your pipe dimensions against standards like B3610 and B3619 to confirm proper sizing. Next, external pressure checks should be performed according to Section VIII, especially for high-pressure applications. Inspection and maintenance are vital, so adhere to API 570 and 574 guidelines to keep everything in top condition. For H2S environments, applying NACE Mr. 0175 or ISO 15156 standards helps manage the risks associated with sour service. Corrosion protection is another key area, and NACE SB 0169 offers practical methods to prevent corrosion damage. Lastly, maintaining thorough QA/QC records throughout installation and testing phases is essential for accountability and traceability. By following these guidelines, we ensure safety, reliability, and compliance across the entire life cycle of our piping systems.